so much for joining us for our first seminar in the 2023 Science in the News Public Seminar Series. We will have 5 such seminars over the next 5 weeks in the same time and same place, so I hope you can join us for some of our future talks. The talk tonight will have 3 parts, and in between each part, we'll pause for questions from the audience. I'll pass around the mic, and if anybody's joining us on the live stream, feel free to type your questions into the chat at any point, and we'll relay them to our speaker. And then after the questions, we'll have a short break, just to catch our breath, get some water, and then we'll start with the next section. Our speaker tonight is Yoony Baek, a first-year physics PhD student here at Harvard. And tonight, he's going to be talking to us about serendipitous discovery in physics. Was it merely a fluke?
Okay, thank you for the introduction, Maggie. Hello, everybody. How are you? Good? Good. Thank you all very much for coming. My name is Yoony Baek. I'm a first-year PhD student in the Department of Physics here in Harvard University. And as an undergrad, along with my major in physics, I was doing my secondary field in philosophy. So this whole field of philosophy of science, history of science, has always been a major interest of mine. Okay, so I hope you enjoy the next hour, and if you have any questions, please feel free to interrupt me anytime. But for those of you who are not comfortable asking questions during the discussion, there's always, the explicit Q&A times, 2 in the middle of the talk and 1 at the very end, so you can use those times as well. Okay, are you ready?
Yeah.
Yeah, thanks for the enthusiasm. Okay, so I want to start by telling you a story about the discovery of this planet. This planet is called Neptune. And this image is taken by NASA's Voyager 2 in 1998. So, as many of you might know, Neptune is the 8th planet in our solar system, and it's the furthest, most distant planet that's away from the sun. Okay, one interesting fact is that Neptune is the only planet in our solar system to be predicted before observed. Okay, so I'm going to tell you like a process of how people got to this prediction and the actual observation. This is a very nice illustration of our own solar system. So here we see our planet Earth, and inside this orbit there lies Mercury and Venus. And in the outer orbit there lies Mars, Jupiter, Saturn, and this, until this point, is the planet that is relatively closer to us, so that it is observable by our naked eye. So because it's easy to see, you don't need any like fancy telescopes to observe. All these planets were already observed by Babylonian astronomers in the 2nd millennium BC, which is from 2000 BC to 1000 BC, so it's like 3,500 years ago, so very long time ago. But there is a giant time leap to the observation of Uranus. It was observed in 1781 by an astronomer / composer named Herschel. And then 60 or so years later, there came the observation of Neptune. But let's go back in time when we didn't know Neptune was there. Okay, so after Uranus, the observation of Uranus, people got very excited that they were calculating the orbit of Uranus and actually observing them, and then see if there are some discrepancies or not. So people thought that Uranus would circuit around this type of orbital path, but what actually got observed was quite interesting. They were seeing some wobbly motions. So there was this discrepancy between the calculation versus the observation. So many astronomers got to thinking, okay, how should we deal with this? How should we solve this problem? And to give you like a context of how the physics or the science status was back in 1700s, it was the great Newtonian physics era. Newtonian physics era means that people all perceived and believed in Newtonian's law of universal gravitation. And it all sums down to this simple formula. When there are two objects with mass, the attraction force that pulls them towards each other can be written in this way. Okay, so there is a problem, right? The calculation doesn't match with observation, and people have to solve this problem. So how did people took this problem? They made a lot of ad hoc hypotheses, meaning all temporary hypotheses, to explain these irregularities. Some of the examples of these temporary hypotheses include observation error, of course, or maybe Uranus was colliding with some nearby asteroids. Or there was like some sort of internal explosion that made this wobbly motion. But one hypothesis that people got very excited about was that there might be an undiscovered planet X that orbits kind of near Uranus that perturbs the orbital motion of Uranus. So after this hypothesis, people assumed that this planet, assuming after this planet X existed, they were thinking of, okay, if this planet existed, where would it be next week, Tuesday, right? People had a lot of calculations to predict where this would lie. And it was actually observed when they, at the specific coordination, at the specific time they predicted. So this has led to the discovery of Neptune, and it became the 8th planet in our solar system. Okay, so this was the story of the discovery of Neptune, but this concept of assuming an undiscovered planet X to explain some abnormal activities of objects that are already discovered, this concept exists till this day. So there is a hypothesis, a very recent hypothesis led by professors in Caltech called the Planet 9 hypothesis. Here, you're seeing an image, you're seeing an illustration with an extremely large length scale. How large is it? Our solar system is like this, very small, right? And all these different objects are revolving around the sun, but one unusual activity that was observed was that they were all revolving very large length scale, but they seem to be clustering at this specific point, which is extremely unlikely to be happening in random chances. Okay, so following from the concept that people thought about in late 1700s, professors in Caltech theorized maybe there's a planet 9, the 9th planet. And if there is a planet 9, there is a way to explain this periodic clustering of this object's very long length scale. And actually, this planet 9 hasn't been proved yet, but it is accumulating a lot of excitement in the field because there's a study that maybe this planet 9 can solve some other existing problems as well. Existing problems, for instance, there is the sun is rotating at a 6 degrees tilt, which is not explained right now, but maybe this planet 9 can be a great attribution to this. It is not solid yet, but I just wanted to make a point that the concept that people tried to solve the problem in few hundred years ago kind of exists till this day. Okay, so from this story, let's evaluate. How did scientists respond to anomalies? Okay, first of all, did they question the Newtonian physics? No, they didn't. No doubts were made on the pervasive paradigm. All the hypotheses were ad hoc, meaning that they didn't think, oh, this wobbly motion of Uranus might be an evidence that maybe Newtonian physics is wrong, right? Those doubts have been made, but the doubts like effects of sun's gravity might be different in great distances, which kind of debunks the whole point of Newtonian description, didn't earn any credit. And all assumptions to solve this problem were made ad hoc. Okay, so what did this attitude lead to? Actually, the scientists persisting on the pervasive paradigm led the discovery of a new planet, Neptune. To elucidate, if people just questioned the Newtonian physics at the very first, maybe this discovery wouldn't have happened so early. So here, we can judge that the critical attitude towards the paradigm wouldn't have led the discovery, which is kind of awkward, right? Because we all learned that critical thinking is at the heart of scientific inquiry. So you might feel a little bit of awkwardness, but hold that thought for a while. We will get back to this. Okay, so switching gears a bit, let's go back 300 or more years ago when people believed the Earth was at the center of the universe. Okay, so from this description, we see the Moon, Mercury, Venus, Sun, Mars, Jupiter, and Saturn, which was the limit where we were able to see through our naked eye. And we thought that all these planets, Sun, and the lunar system all revolved around us. And this belief is known as the geocentrism. It's a belief that Earth is fixed at the center of the universe. So who initiated this paradigm? It was Aristotle. So in one of the writings, books that he wrote, he says the Earth does not move and does not lie elsewhere than at the center. Okay, so it lasted until late 1500s. So you can see that there was almost like more than 2,000 years in human history where we had a firm belief that Earth was at the center of the universe. And this was the point even before Newtonian physics. Looking at this more simple diagram, I wanted to briefly mention you like the brief history between geocentrism versus heliocentrism. Heliocentrism meaning this saying that a belief that says the sun is at the center of the universe. Okay, so there's a timeline. So according to records, Aristotle in 350 BC said, kind of initiated this whole paradigm into words. But at 250 BC, a philosopher not quite well known called Aristarchus has mentioned that maybe we are not at the center of the universe. And the reason for that was, sun is just too big to be rotating around Earth, and he has a point, right? Sun is quite large to be rotating around us, but of course this was not enough to convince people at the time. However, there has been an accumulating mystery under this geocentrism, and there are many, but one of the representative ones are the retrograde motion of Mars, which means that when we track the position of Mars every night, we would assume that according to geocentrism, it will move in one direction, right? But periodically, it was going backwards and then going forwards again. So in order to explain this, you have to come up with another hypothesis or another theory, right? So just having this simple diagram wouldn't solve this problem. So how did people back then solve? In 150 years, Ptolemy seemed to have solved the problem. And the way he responded to this problem was very similar to the discovery of Neptune. He persisted on the current paradigm. He persisted on geocentrism. And then he introduced the concept of epicycles. Epicycles are these small cycles that locally, when we see locally, Mars will rotate around this circle, but this circle itself is revolving around Earth. This seemed to be a very clever idea because according to if we are having like a right amount of size of epicycle with the rotation speed, it could be explaining this backwards motion. Okay, so even with introducing like some epicycles, more abnormal observations accumulated. And what people did to solve each problem was to just introduce another epicycle. So like epicycle on epicycle on epicycle. There was an accumulation of ad hoc hypotheses for about like 1500 years. But in 1543, it was like, enough is enough. Nicholas Copernicus claims that Sun is at the center of the universe and Earth is the one that's rotating around it, revolving around it. So back then, how did Copernicus earn people's attention? When we placed the Earth in the center of the universe, the Sun, along with 7 other planets, would revolve like this. And this motion is explainable if we introduce like 1,000 epicycles, right? But when we place Sun at the center of the universe, it becomes this simple diagram. And not long past that time, Newtonian physics came into play, and then people were all asserted by this heliocentrism. Okay, so let's evaluate this scenario again. How did scientists initially respond to anomalies? Like initially, meaning a very long period of time for this one. Very same as the story of Neptune, people didn't doubt the existing paradigm. They firmly believed that geocentrism was right. So all assumptions, for instance, introducing the concept of epicycles, were all temporary, all ad hoc. However, in this case, different from the discovery of Neptune, scientists persisting on the pervasive paradigm, which was geocentrism, delayed the scientific progress. So in this case, maybe critical attitude towards paradigm would have led earlier discovery. So when we compare these 2 different stories and ask the same question, here are the following. To have a real rapid recap, for this Neptune story, the existing paradigm was Newtonian physics. And for this geocentrism story, the existing paradigm was geocentrism. And it all kind of ignited with some sort of anomaly, right? Some abnormal observation. What was the abnormal observation? For the discovery of Neptune case, the observed orbit of Uranus didn't match with the calculated orbit. In the case of geocentrism, one of the anomalies was Mars showing retrograde motion. So let's ask a question to ourselves about this one. Were there efforts on maintaining the existing pervasive paradigm? In the Neptune story, yes, right? They didn't doubt Newtonian physics, they persisted. In geocentrism, also yes, people have just firmly believed geocentrism for more than 2,000 years. So both answers are yes. Now comes the important question, which is, did this anomaly change the paradigm? Did the discovery of Neptune change the paradigm of Newtonian physics? No, right? for what it's worth, it even strengthened Newtonian physics. It made people to believe more in a more believable way about Newtonian physics. But for this geocentrism case, these anomalies actually changed the paradigm. So when we assess all the scientific discoveries made in the past years, many of them can be categorized into these two different parts. This part is called the normal science, where anomalies did happen, but it ended up to strengthen the existing paradigm. But for anomalies that made contributions to change the paradigm, we call it the revolutionary science. And these concepts were introduced by Thomas Kuhn. Okay, so as Maggie mentioned, our talk is composed of 3 different parts. Actually, I'm almost halfway done with part 1. So in the remaining part of part 1, I'm going to kind of elucidate more about Kuhn's view of progressing science. In part 2, I'm going to introduce you a very interesting recent anomalous discovery in physics. And for the last part, I'm going to talk about the implication and some limitations or skepticism people have about Kuhn's view. Okay, so I'm first going to introduce who Thomas Kuhn is. I already have been saying this word paradigm a lot, but I'm just going to give you like a more rough definition of what paradigm is, and to tell you more about normal science and revolutionary science. Okay, so I introduced you Thomas Kuhn. He's an American philosopher of science, and he did his bachelor's degree, master's degree, and PhD in physics at Harvard University. Yeah, there is already a hint because I wrote down bachelor's degree as AB, and I got this is like a Harvard thing. Yeah. So he did all his higher education in Harvard. He was the editorial chairman of the Harvard Crimson, which is the Harvard newspaper. And he was led by James Conant, who was the former president of Harvard back then, to become a historian of science. Many of you might be already familiar with the name Conant because it is the name of one of the GSA storms, Conant. He wrote a very famous book in 1962 called The Structure of Scientific Revolutions. After finishing his degree in Harvard, he went on to Berkeley. Yes, he went on to Berkeley and became a professor there and wrote this book. And one very fun fact, which is kind of irrelevant to my talk, is that he interviewed Niels Bohr the day before Bohr died, which is a very interesting fact, which is very relevant. So this book is evaluated as the most frequently cited book written in 20th century, which is kind of a bold statement, right? Which also shows the power of how this book kind of revolutionized how we view science. And this book popularized the idiom paradigm. Okay, so what is paradigm? Paradigm is a philosophical word that has so well immersed into our everyday dialogue. Okay. To give you like a definition that Kuhn made of what paradigm is, he wrote, it's a universally recognized scientific achievement that for a time provide model problems and solutions to a community of practitioners. Okay, it contains so much important information, so I'm just gonna read it out again. Universally recognized scientific achievements that for a time, it's not permanent, for a time, which already implies some temporariness, provide model problems and solutions. And these are the activities that happen during normal science. To a community of not scientists, he explicitly said as practitioners. which means that this paradigm has a lot of relevance to what's actually used in our everyday lives. One main criticism that Kuhn is always suffering from is that in his book, this word paradigm is used in so many different meanings. To my knowledge, it is like used in 12 different contexts, but we can roughly divide them into two parts. A narrower definition would be the exemplar, so like the theory itself, and a broader definition would be a disciplinary matrix or like a framework. It all seems kind of abstract, so I'll give you an example. In this case, when we just use this formula itself without questioning whether this formula is right or wrong, if we just use this formula to solve any problems, we are using this theory itself, right? We don't think about like implications of this. We just use this formula itself. So this is when we use this paradigm as an exemplar. For the second part, we mentioned geocentrism versus heliocentrism. And heliocentrism is a belief that sun is at the center of the universe. But maybe some of you have already kind of thought about that. Actually, sun is not at the center of the universe, right? So, strictly speaking, heliocentrism is also wrong because sun is not at the center of the universe. But why is this so important? Here, it is the framework that matters. It is not that sun being at the center of the universe is important, but it is such that Earth is moving around somewhere. It is that framework that matters. So in this context, the paradigm is used as a framework or a disciplinary matrix. Okay, so let's take a look at Kuhn's view of progress in science. As time passes by, actually most of the time is composed of normal science. And normal science is a time where regular work of puzzle solving, you can just think of as doing piece sets. Puzzle solving activities within a settled paradigm. But one important thing here is that there are these small intervals, which is called the revolutionary science, where the breakthrough activity that allows a dramatic advance in understanding happens. And this dramatic advance in understanding can be rephrased as a paradigm shift. So when we start with the normal science 0, I'll just call it NS, normal science 0 under the paradigm 0, we happen to meet revolutionary science. And after meeting this revolutionary science, normal science follows under another paradigm, which I would call paradigm 1. And then another revolutionary science comes. Then the following normal science follows another paradigm, and repeat. Okay, so in one sentence, Kuhn's view of progress in science is that it is not a uniform process. It is not a uniform progressive process, but it has an alternating normal and revolutionary basis. One key important fact is that, okay, so what happens during normal science that ignites this revolutionary science? Are they independent? They are not independent at all. So let's take a closer look at a single normal science era, which kind of ignites the next paradigm, the next revolutionary science. So what happens during normal science? First, under the new paradigm 1, a lot of observations are being made, but some people might find some unexpected observation. But more often than not, it can be explained by paradigm 1, where we can learn from the Neptune story that many of the anomalies can actually reinforce the paradigm. But as time passes by, some unsolved observations kind of accumulate, and when it reaches a threshold, there comes a paradigm crisis, and these unsolved anomalies ignite the revolutionary science. Okay, so during this normal science, when we just say normal science, it kind of sounds boring. It seems like not a lot of exciting exciting scientific developments happen, but actually normal science is undergoing an extreme tension between research versus education. Here, research meaning people want to find new things, right? People want to find like new anomalies. Where when we think of education, when we think of like education we have gone through during our middle school or like high school years, we were taught with the paradigm, right? We were taught with the Newtonian physics, the existing paradigm. So education is kind of more in a conservative way, but the research is in kind of a more, revolutionary, exciting way. And this tension is well described in Kuhn's second most famous book, titled The Essential Tension. Okay, so to give you a hint about the upcoming part 2, I'm going to explain on a current unsolved anomalous observation, so stay tuned. Okay, before wrapping up, I wanted to share an analogy with you that what it feels to undergo a paradigm shift. Okay, so I kind of already showed you the image, but at first glance, tell me what you see at first glance. What do you see? Yeah. Head of a deer, right? Don't look harder, just at first glance. Okay, I'm going to rotate this upside down. Now what do you see?
Seal?
Yeah, a lion seal. Okay, so I'm gonna turn this upside down again. No, you see like the head of the deer and also the flipped lion seal, right? So for those of you who only saw the deer at first, you're in a totally new perspective right now. So it's never before. And this like optical illusion images are the ones that people make a lot of analogies to help other people understand how it is like to go through a paradigm shift. So after the paradigm shift, your view of the world is never like before. Yeah. So as a recap, we have looked at 2 examples of scientific discovery, which was the Neptune story and the Geocentrism story. And each of the story is a great representative of what's happening during normal science and revolutionary science, respectively. We also looked at the definition of paradigm, which was universally recognized scientific achievements that, for a time, provide model problems and solutions to a community of practitioners. And last but not least, we looked at what Thomas Kuhn's view is, which was the progress in science is not uniform, but has alternating normal and revolutionary phases. So before getting into part 2, I'll break for some questions. Yes. Oh, sorry.
Oh, sorry. Yeah, thanks so much for the great introduction. I just wonder whether, like, as a scientist who is in the phase of the scientific progress, like, can we determine whether we are in the normal science phase or the revolutionary science phase?
Yeah, that's a really good point, because it's hard to know whether we are in a revolutionary science phase or in a normal science phase right now. It's always some years later when we look back that, oh, we were at the normal science. Oh, that was the revolutionary phase. So it's kind of hard to tell where we are at right now. But as I am going to continue talking about, having a view of what's anomalous, what's the current paradigm, having an exact understanding of what the pervasive paradigm is very important to evaluate if the new discovery is anomalous or not. Thank you for the question.
So I was wondering, since it seems like Kuhn studied probably like in the 50s and 60s in physics, I'm wondering, how much of his view was kind of inspired from the revolutions in special relativity and quantum mechanics that occurred at the start of the century versus, how much of it was maybe just like a more
Yeah.
broad view of science, from 2,000 years ago all the way to now.
Yeah. I'm actually not sure like what he researched on during his PhD, but as I mentioned, like the president back then kind of led him to be a historian in science. After his graduation in PhD, this might not be like relevant to your answer, but after his PhD, he remained in the Harvard University as a lecturer, and he was making textbooks. So this was when he kind of thought about these all puzzle solving activities that happens during normal science, and this idea arose him to kind of differentiate these two different phases in the history of science. But, yeah.
In the example that you presented, the comparison between the Neptune example and the geocentrism versus heliocentrism, you said that one changed the paradigm and one didn't.
Yeah.
What is the assessment there? Who's deciding, or is it the reception of society to those paradigms that decide whether this is shifting the paradigm, or are there other influences that result in this change?
Yeah, that is also a really good point. Who evaluates that, right? I don't have a good answer for that right now. I think the consensus that people make in these academic arenas might be responsible for that, but yeah, that is also a very good question to like keep track of. Thank you. Yeah.
I'm just curious if there's any degree of a revolutionary science, because every work is somewhat revolutionary on their own field.
Yeah.
So, and is there any work by Kuhn or some others that try to quantify the revolutionariness, or is there any view that says normal science is small revolutionary?
Right, yeah, I see what you're saying. So, well, it is obviously very hard to quantify the increment of the development. But one thing that always happens, like just at the boundary between normal science and paradigm shift, is that there is a fierce competition between two paradigms, one being the new one and one being the existing one. And when we look back at history, when we look at like general relativity, we can also observe that those competing stages were present, but there's always like this defining observation that evaluates like which paradigm wins. So in general relativity's case, it's the Eddington's the observation picture that kind of evaluated the acceptance of general relativity. So within the revolutionary science, it's such a short period of time. So I'm not sure if people also divide it into different steps, but one common thing is that at the boundary, there's always this competition between two different paradigms. Yeah, thank you for the question.
Okay, we'll take two more questions, I think. More people, and then we'll start.
I guess my question is kind of similar to the previous one, but how do you know what is a paradigm? So for example, in the case of the Neptune discovery, how do we know that the paradigm wasn't that there's only 7 planets and there was tension between, maybe Neptune or Uranus was hitting the asteroids versus the new paradigm that there was another planet? Why are we defining this paradigm in that case specifically to be the gravity as opposed to some other part of the theory?
So are you saying why new paradigms didn't receive much attention back then.
Like why, like looking back, we're saying, you know, discovery of Neptune did change the paradigm that like Newton's like law of gravitation.
Yeah.
But it did change the concept that there was only 7 planets.
Yeah, yeah.
So that's could be viewed as another paradigm, and then the tension would have been between like all of those ad hoc hypotheses.
Mm-hmm. Mm-hmm. Yeah, that is also a valid point. Yeah, I see your point. Like, but in this like specific case, maybe Newtonian physics has much more, you know, universal meaning than having like a 7 planets in. So I don't know. Like maybe we can always kind of relatively say which one is, you know, more should be more viewed as universal, whereas which is has like less scientific grounding.
Yeah, thank you for a nice introduction. So I was probably focusing a little bit on your discussion of when Copernicus started to talk about geocentrism, and you motivated it from the fact that from the
Heliocentrism?
Yeah, what was the small cycles that when you
Epicycle.
Epicycles,
Yes.
So you're saying that there were so many epicycles to fully explain it.
Right.
There's a whole bunch of planets and are so complicated.
Yeah.
And then Copernicus said, yeah, like some center is simple.
Mm-hmm.
But what if the epicycle theory could actually predict the correct epicycle to describe a new planet? Will it last longer?
Yeah.
And
Yeah.
sorry, you know.
Yeah, actually, introducing epicycles created a more precise observation, actually. So, going back to Copernicus' case, when we just viewed sun as the center of the solar system, or back then like the center of the universe, the observation, that the calculation that people made back then was, you know, actually less precise. But it was just that it's so much simpler. So how Thomas Kuhn viewed this like paradigm shift was that, okay, introducing epicycles, we cannot consider that as a wrong theory, right? Because it is just how we view in Earth, right? So Kuhn says that no paradigm can be fully proved because, you know, it's just the view of what we view nature. But what we can do is that a new paradigm can shift us to another level to view things differently. So going back to your case, yeah, if epicycles were having a strong theory enough to predict random, like undiscovered back then objects, maybe there might have been a elongated competition between the theories. But I'm not sure how that might have ended.
All right, we'll take questions at the next stopping point for your part.
Yeah. Okay. In the interest of time, I'll just keep going. But please feel free to, you know, hang around when people are asking questions. So, okay, going to the second part of the talk, I'm going to introduce you a recent anomalous discovery in physics. But before getting into that, I wanted to kind of, you know, give you a taste of where we are getting at. So I'm going to briefly explain you the different areas in physics, and then explain the discovery of superconductivity in ceramic materials, which was discovered in 1986 and received a Nobel Prize in Physics in 1987, which is a record fast thing. Okay, so as you may remember, I was going to come up with part 2 with this part, right? Before getting into that, I wanted to briefly explain the different research areas in physics, because physics itself has so broad disciplines. Okay, there are a lot of ways to categorize different research fields of physics, but one idea that we can get from is from this unity of science concept. It's a concept that says all the science are formed as a unified whole, which means that there is no, clear boundary between different fields of sciences. In this book, they categorize with different length scales that we are living in. So I'm gonna follow the same evaluation to discretize the areas of physics. So from very small length scale to a very big length scale, to give you a sense of how small it is, nanometer is like in the size of atom, and micrometer is in the size of a living cell. So yeah, you get the idea. In both ends, in like astronomical units, fields in physics that is concerned with this length scale is called astrophysics. And in the very smallest length scales, concerning with subatomic particles are called as particle physics. And in the middle, there are soft condensed matter physics, also known as, mostly called as biophysics, which usually are interested in the above range of micrometer. But between this micrometer and nanometer, where atoms aggregate to form living cells, there is atomic, molecular, and optical physics, also known as AMO, and the hard condensed matter physics. So the recent anomalous discovery that I'm going to talk to you about lies in this field. So it might be good to keep in mind that we are looking at this nanometer to micrometer length scale. Okay, so discovery of superconductivity in ceramic materials, which was discovered in 1986, about 30 years ago, right? So much more recent than the two examples that I showed you earlier. But before getting into the superconductivity, I just wanted to give you a good motivation on why we should care about this. These are utility poles, and they carry electrical current from the supplier to where we are right now, to consumers. But during this process of transmission, 15% of power is lost. So this power loss in transmission can be a very unique way to solve our current energy issue in Earth. So in order to reduce this power loss, we should think of where does this power loss come from? So where did the 15% of power go? It is all lost through heat, which we cannot collect back. So let's take a look at what's inside the transmission wire. As I said, it is in the field of hard condensed matter physics, so we are dealing with atom by atoms in a length scale. So inside the wire, there are atoms, and if it is were to create a nice electrical current, it should contain electrons. Where does this electron come from? It is being freed by one of the atoms, by one of each atoms. So each atom would form this plus sign as opposed to electrons. So yeah, this is our basic platform inside the wire. Okay, so the current is the flow of electrons. So when we think about electrons actually moving inside the wires, let's take a closer look at what happens here, where this electron seems to be colliding with one of the nucleus, right? Or charged atoms. What happens is that it hits and creates heat. Because it has created heat, the charge after the collision loses energy. So these are all accumulated to have this 15% of energy loss. So this is where the superconductivity concept kicks in. It is a physical state where electrons can flow inside the wire without having a collision with charged atoms. Because it doesn't have any collision, there is no heat loss in this material, which is like really nice, right? Because we would have like 0% power loss. But the problem is that this physical phenomena only appears at very, very, very low temperature. Let's look at the very first superconductivity found in the human history. It was mercury. It was mercury that was discovered as the first superconductor. And how you should read this diagram is that the x-axis is temperature with a unit of Kelvin. And the y-axis is resistivity, but here you can just think of it as heat loss. So when reducing the temperature, the heat loss does decrease, but at some point it reaches 0. Not a small value, like 0. And this is when we say the superconductivity has arisen. We call this temperature, there are multiple names to call this, but I'll just call this as the threshold temperature. And for mercury's case, the threshold temperature is 4.2 Kelvin, which is minus 269 Celsius. And for those of you who are more familiar with Fahrenheit, if it helps, it's minus 452 Fahrenheit. You can kind of have a sense that it is extremely cold temperature, but how cold is it? Let's compare it with the coldest place on Earth. Can anyone guess the temperature of the coldest place on Earth? Any guess?
70 below.
Minus 70? Lower than that. So it's in Antarctica. The coldest place on Earth has a temperature of minus 94 Celsius, which compared to minus 269 Celsius is a very hot temperature. Right? This is just to give you a sense of like which temperature range we are dealing with. Okay, here's another question. There are 118 elements in the current periodic table. How many of them do you think are superconductors in low temperature? Any guess? 15? Okay, yeah, that's a lot. It's actually a little bit smaller than that. 31 elements in the existing 118 elements, that is, in the current periodic table, are superconductors at ambient temperature. So in this table, you can just take a look at the green ones. Okay, so 31 elements out of 118, it is more than 25%. So actually, superconductors are very common in the planet Earth. But why are we still suffering from this 15% power loss? Because as a single element, the highest threshold temperature is found in niobium. And the threshold here is 9.25 Kelvin, which is minus 264 Celsius. And remind you that the coldest place on Earth is above actually minus 100 Celsius. So after people have kind of sorted out what elements are superconducting and like their threshold temperature, people found out that, okay, this is very difficult to incorporate in our everyday lives. So did people just give up? No. They came up with different compounds of different elements. And when you mix different elements together, you may have a higher threshold temperature. So this was the connection people were getting at. So starting from mercury, which was found to be superconducting in 1911, I mentioned you that niobium was the highest temperature superconductor as a single element. So starting from this niobium case, people started to leverage this threshold by, okay, before getting into that, I wanted to mention that this liquid nitrogen temperature, which is 77 Kelvin, which is still extremely low temperature, is very accessible in our experimental labs. So if you go around like physics labs or chemistry labs, it's kind of easy to see these barrels. So the things that are inside this are in the temperature of this one. So experimentally, this value would be a very accessible limit. Okay, so after people have sorted out that niobium is the highest has the highest threshold superconductivity, people have been making a lot of compounds out of niobium. And it was an incremental development, but at this time when people got stuck with niobium-3 gallium, it didn't seem to go anywhere else. But in the year 1986, two researchers in IBM found a new class of material that has revolutionized the threshold temperature of superconductivity. For this material, we can first see that, okay, it is a very complex one, right? It's not even three, it's a combination of 4 different elements. But one common aspect is that they all contain this copper and oxide. And the class of material that has copper and oxide, we call it as cuprates. So these are the two scientists that received Nobel Prize in 1987, 1 year after the discovery of this cuprate. Okay, I mentioned cuprate as the material having copper and oxygen, as a copper oxide material, but okay, so it is a material, right? And we're living with materials every day. So what is it in our everyday lives? We can take a look at how they were referred in the Nobel Prize Committee. They were awarded for their important breakthrough in the discovery of superconductivity in ceramic materials. So there's a word that we use in a daily dialogue, right? What's a ceramic material? Yes, it is the material that is used to make pottery. When you think of pottery, it's a non-metallic, heat-resistant material. So for it to become superconducting, it should be flowing current, for flowing electricity very well, right? But this might seem like the least likely candidate to be a superconductor. Okay, so going back to the title of my talk, was it really a fluke? If I just ended my talk with this story, you might all think, wow, that's super cool. It might have been just a fluke. It might be just been by accident. And maybe lots of news articles might like this story, but it is necessary to look back at how people got to this cuprate material. It had some context in it. Okay. Yeah. Since we were all talking about the normal science, paradigm, revolutionary science, let's kind of adapt that concept to our current superconductivity field, right? When people were finding all different sorts of niobium compounds, there became a very solid theory explaining why superconductivity happens in this material. And it was published in 1957 by 3 physicists / mathematicians, Bardeen, Cooper, and Schrieffer. And we call this theory as the BCS theory. And in the field of superconductivity, we can kind of view this BCS theory as the current paradigm. Okay, so what did Kuhn ask us to do after knowing this paradigm? We should kind of believe in it, right? And in order to believe in it, we should know what BCS theory is. And it seems very difficult, but for me, it is one of the few advanced theories that can be understood kind of in a very conceptual way. Okay, many of you might already know this concept, but bear with me. The concept of BCS theory can be explained by PowerPoint slides. Okay, so let's go back to this inside the wire world, where there are these charged particles, and there is an electron that carries current. Okay, so we all have learned that minus attracts with plus, right? Plus charge. So this electron is a minus charge, and each atoms are charged as a positive ion. So we can very naturally think of the interactions between this electron and the neighboring atoms, which I would call as electron lattice interaction. The lattice meaning the whole combination of these blue charged atoms. Okay, so what happens because minus attracts plus, plus attracts minus? This charge is able to make a distortion in the lattice, which means that it can create these plus ions to be forming closer to them. So when this happens, electrons were still moving, right? When this electron has moved further, it has created this accumulation of dense plus ions macroscopically compared to other regions. So in the view of the later electron that was approaching. Okay, so for the later part of the electron that was approaching, since there is a dense area of plus ions, it gets attracted to this region. And very surprisingly, these two electrons form a pair called a Cooper pair, which is from the Barton-Cooper-Schrieffer. And after forming this Cooper pair, these two electron pairs move together. So the basic concept of the BCS theory is understanding Cooper pairs. And it is the electron-electron pair that is made possible by lattice distortion through electron lattice interaction. So here what I want to emphasize is that the lattice distortion is very important to create this Cooper pair. Okay, so this is the basic ground that for the development of new materials. Okay, so let's think about how this lattice distortion were made. How were these made? It was the electrons that were making these distortions, right? So let's think of it as this way. Okay, so inside the superconducting wire, there is a Cooper pair that forms kind of a macroscopic state, and the lattice are, we can see that the lattice are distorted. Okay, here comes the question. What if the lattice is already distorted? What if the lattice is distorted not from the electrons, but what if the lattice itself was already distorted? What I mean by this is that take a mind that we started with this picture, right? Where we had a homogeneous atom, C. But what if a material already had this distortion? Would it be more beneficial for electrons to form Cooper pairs? Maybe it could be a better way to form a stronger Cooper pair. So this was the whole initial idea of people trying to make new type of materials where the lattice was already distorted. Search for new materials. What type of materials? Materials where the lattice was already distorted. And in a more kind of scientific sense, this distorted means that the lattice is not symmetric. Why was it so difficult to find this material? It's because nature loves symmetry. And we can find these symmetrical images everywhere in nature, including honeycomb, snowflake, even the large objects in sun, moon, or in like flowers. Because nature loves symmetry, in a molecular level, we would also assume that atoms aggregate together in a very symmetric way, right? But luckily, okay, before getting into that, nature loves symmetry because, not only because symmetrical shapes are beautiful, but nature prefers symmetry because it is energetically stable. Okay, but fortunately, there are some structures in materials where the material gives up the symmetry. It doesn't follow the symmetry to minimize its energy. Materials that gives up symmetry to lower its energy, in a technical term, is called the Anteller distortion. And this structure, more often than not, can be found in octahedra units. Octahedra is a shape that looks like this. So this is a very symmetric shape of octahedra, where there are 8 corners, 8 triangles, but there are some combination of materials which would prefer the distorted ones rather than the symmetric ones. And the most well-known combination that forms octahedra in a distorted way is a combination of copper and oxide. More specifically, the oxidation state of copper has to be copper 2+. What if it's 3+? It forms a totally symmetric state. Okay, so to kind of recap on that, the distorted octahedra is energetically favorable for copper 2+ oxygen. So copper 2+ kind of prefers to have a distorted one. Whereas copper 3+, very conventionally likes the symmetry, and it forms a symmetrical octahedra. Okay, so here's kind of a direction that we can take. What if we can make a combination of copper 3+ oxygen and copper 2+ oxygen? I mentioned that copper 3+ likes symmetry, so it creates a symmetrical octahedra, whereas copper 2+ likes this distortion. So if we make a material that is combined with copper 3+ and copper 2+, we can maybe make a distorted lattice. So this is kind of the whole concept of the idea. When you look at these planes, because these distorted ones are kind of elongated, when you look at the view from the top, you will see like smaller squares for copper 2+ and bigger squares for copper 3+. Okay, so let's go back to the distorted lattice case. Okay, I don't know how many of you would have noticed that, but we can actually cover this pattern with 2 types of square, the big one and the small one. So if we create a material that has both copper 2+ and copper 3+, we would have made an already distorted lattice that might be beneficial to have more stronger Cooper pairs. Okay, so the next question is, are there materials that contain copper 2+ and 3+ in the same material? And the answer is yes. The first major discovery found was in 1981, and keep in mind that the discovery of cuprates happened in 1986. Okay, so in 1981, 3 scientists in France, 3 French scientists have created this crazy material. You don't have to, of course, know all each components, but the important part is that it contains both 2+ and 3+. Another important discovery by the same group was found in 1985 by another very complicated material, So here the copper is not explicitly mentioned as this one, but this copper, some of it is 2 plus, and some of it are 3 plus. Okay, so these two compounds are already a material having both copper 2 plus and 3 plus. But these materials itself were not superconducting. Actually, the first one was an insulator. Insulator meaning materials that don't allow electrons to flow. However, this discovery of a mixed copper 2 plus and 3 plus material in 1985 is a conductor at room temperature, which means that it flows electrons very well. So in order to make a superconductor, it might be a better way to start with a conductor, right, rather than an insulator. This was the exact process that Bednorz and Wheeler followed. So what happened during this short amount of 3 or 4 years? On the left side, I'll explain the discoveries made by the 3 French scientists. And on the right side, I'll mention the ones that were discovered by the Nobel laureates. Okay, so in 1981, they discovered this crazy material which had both copper 2 plus and 3 plus at the same compound, but it was insulator. At 1983, these 2 researchers in IBM launched the search for a new superconductor. In 1985, as I mentioned before, these 3 French scientists have discovered this metallic state of mixed copper oxides. The important part is that it is metallic, so it was enough to create a lot of attention to the field. So what were they doing during these 2 years of gap? They were actually interested in nickel oxides. They didn't start with copper oxide, they started with nickel oxide. But for these 2 years, they were not getting any superconductor for this nickel oxide. After the discovery of this metallic mixed copper oxide made in 1985, it motivated them to study this material and tune the ratio of copper 2 plus to copper 3 plus by changing the baryon concentration, blah, blah, blah. But this motivated them to start with this material and then kind of play the stoichiometry between them. And what happened? They discovered that superconductivity incorporates in 1 year, and then the next year they received a Nobel Prize. To claim that I'm not telling you a lie, this is a memoir. This is not a research article. This is a kind of memoir, kind of review perspective, written by the 2 Nobel laureates in science. This was actually published like 2 months before the announcement of the Nobel Prize. But during those 1 year, it was enough to create a super influence in the field. So let's just read this together. Okay. At this stage, we became aware of a paper by Michel Araujo and Raviu. This reference 29 is this paper. On the mixed perovskites, this material, which is exactly this material, right? Exactly meeting the requirements of mixed valency. Mixed valency meaning having both copper 2 plus and 3 plus. Okay, the French authors, these 3 people, had shown that this mixed oxide, a metal at room temperature and above, contain both copper 2 plus and 3 plus. Thus, we tried to reproduce it, at the same time continuously varying the ratio between copper 2 plus and 3 plus by changing the baryon concentration in this material, and we looked for superconductivity. For those of you who are kind of interested, who got to be interested in this topic, please Google Jahn-Teller distortion or Jahn-Teller physics and cuprates, because it's a whole thing. Jahn-Teller physics and high TC superconductivity, if you just read the first sentence, the discovery of high temperature superconductivity in cuprates was not accidental, but was based on the knowledge that divalent copper ion, which is copper 2+, is one of the strongest Jahn-Teller ions, meaning that the copper 2+ likes distortion. So let's go back to this question. Was it merely a fluke? Now your view might have changed, right? Maybe I have convinced you to say that, okay, it is not a fluke. It is not some random material that popped up out of nowhere. Okay, so why did I mention this as the anomaly? Because even though the whole motivation started from this BCS theory, right? It is indisputable to say that. But there are a lot of things that this theory, the current paradigm, cannot explain the physical phenomena happening in cuprate. And one of the physical phenomena that people cannot explain is this high superconducting threshold temperature. So in a very simple words, this theory cannot calculate that this material has a threshold of 100 Kelvin. So maybe this might be, solvable in the future. We don't know yet, or maybe some new theories that are actively coming up might replace BCS theory. We don't know it at this stage. But what we can learn from here is the importance of normal science. The way we can evaluate this is that the deeper understanding of the existing paradigm, which is BCS theory, led to the discovery of a new class of superconductors. Here, the deeper understanding means that not to question the paradigm, not to just debunk the BCS theory right away, but to have an extending scope of paradigm rather than challenging it. Here's a short interview from Kuhn saying that Kuhn recalls students approaching him to say, "Oh, thank you, Mr. Kuhn, for telling us about paradigms. Now that we know about them, we can get rid of them." So you can now evaluate that this student had a totally misunderstanding of what Kuhn was saying, right? He just regarded normal science as the bad thing, and he wanted to create a paradigm shift. Kuhn responded, "In retrospect, I begin to see why this book, which is the structure book, fed into that, but boy, was it not meant to, and boy, does it not mean to." So that was part 2. I'm not sure how we should proceed.
Take maybe 1 or 2 questions,
Yeah.
but yeah, given the time, perhaps it'd be good to get shortly. So 1 or 2 questions.
Thanks. I just want to channel attention to the unsung French heroes, how did they motivate their research and what made them not discover the high DC superconductor?
So what's the last part?
What was the motivation of the French research groups in studying the cuprates? And along that line, why didn't they discover the superconductor?
Yeah, so they were studying this mixed copper 2+ and 3+ material, actually in a very totally different aspect of the field. They were not interested in getting to know the superconductivity, but in the field of oxides meaning materials containing oxide, a lot of trends back then were kind of focused on structural changes that induce physical property changes. So this copper oxide having this mixed valence state were known to have some structural phase transition along the temperature, and they were just trying to see how those structural differences would induce different physical phenomena in ferroelectricity or something like that. Of course, superconductivity also can be viewed as the physical properties, but their focus was on a totally kind of different field. So Bednorz and Müller were very clever enough to adapt that idea of material synthesis into their own work.
One more question.
Very nice talk. I want to ask your opinion on recent discovery of room temperature, vapor pressure, conductivity. So, what do you think is this fit into the frame that you, this fit into the frame you have talked about?
Yeah. To my knowledge, they are all based on BCS theory. So to give you like a context of what's happening these days, there was a great theoretical prediction that if you put an enormous amount of pressure to hydrogen, if you think of hydrogen, it's like the simplest atom we can think of, right? It's the atom number 1. If we put like enormous amount of hydrogen and make it like as a solid form, it might be metallic or even superconducting. But since material composed of just hydrogen is, very simple, it can be like explained by BCS theory. But in order to make this hydrogen solid, we need pressure that's being put in the core of the Earth, which is like in a very harsh environment. So in order to make it like more accessible experimentally, people have been started doping the hydrogen with a very, very, very heavy metal element. And if you chemically dope it, you can kind of induce this physical pressure in a chemical way. So this chemical pressure can induce a very high amount of physical pressure. So people have been trying to discover like this new type of like lanthanum hydride, where lanthanum is replacing the hydride. Lanthanum is one of the like heavy elements. And the recent discovery that Sam has mentioned is that a group has realized that they can fully replace the physical property with chemical doping. My view is, I'm not sure, because it's recorded on YouTube, but yeah, I'll just say, I don't have much background in the field, so we'll just, have to see. But yeah, it's hard to just disregard it because it is published, and they say they had 5 or 6 times of revision. So I don't have a good assessment for that right now.
Okay. In the interest of time, if you have other questions, maybe we'll hold them until the end of part 3
Okay.
and chat afterwards.
Yeah. Okay, so it's already 30 minutes past time, but thank you all very much for your engagement. But yeah, I don't mind if you have to leave with other occasions, but so please feel free to stay out or stay on. So
If you do have to leave, you can always catch the end of this on YouTube later.
yes, there you go. Okay, in the last part, I want to mention the implication and some current skepticism that people have on Kuhn's view. So very simple sections. I'll start with some philosophical implications that we can make based on this Thomas Kuhn's idea. We have looked in very detail about these 3 different episodes, right? On the first part, we looked at the Neptune story and the geocentrism story. And the second part, we kind of delve into this history of the discovery of superconductivity in ceramic materials. And the point that I want to make is that Kuhn emphasized on the importance of learning the history of science. And I strongly agree with this, because it makes us understand better about the existing paradigm. Just take a look at this cuprate superconductor, for instance. When I just told you there is this discovery, and when I just told you about the results, that itself is also a scientific knowledge, but how do you feel like after having heard the history of that was in the background? You kind of feel you're like following the context of what discoveries are actually being made. Right? More important things is that when we look at the history of science, or when we follow the steps of how the development is made, we can get new ideas from the thought process. And one major example was that the concept that people used to discover Neptune is still like used to this day, even though it wouldn't, even though like the text itself would be different, the concept can be like renovated enough to excite the later scientists. Here, Kuhn emphasized so much about this process and compared this with the result. So rather than just knowing what the result is, it is so important to take a context knowledge of what the process was behind that. And one kind of funny thing, interesting thing that I found was that, so this is the Nobel Prize winning paper, which is cited 20,504 times, Google Scholar based. But for the discovery of material that has become like the parent material of this one, the 3 French scientists, the citations is 214. And part of it, I think, is because if it was not for the memoir article that was published in Science, maybe not many people would have known this story. Because when you just read this paper, of course this cites this paper, but it cites in a very specific like sentence of like some very specific like X-ray diffraction, stuff like that. What I want to say is that this was not deemed as a motivation to this study when you just read this article. So, how can we get to know more about the thought process? When you look at the storyline of a general research article, I was so influenced to take this thought process by watching this YouTube video of a lecture given by Professor Peter Abamonte in the University of Illinois Urbana-Champaign. He's a physics professor, and this seminar is titled How Laws, Sausages, and Science Are Made, an inside view of how science really works. It's an hour-long video, and I strongly recommend you to watch this. Like, it's so enjoyable to watch. In the middle of the talk, he gives a pitch about like how the storyline of the research article are actually being made. You start with a question. You might think of there might be some answer to that, right? And your like ideal goal is to start with a question and arrive at the answer. And this might be a good research article. But what actually happens is that you start with this question, but along the way you see some like unexpected findings. And more often than not, you find yourself placed in a situation where actually this question doesn't make sense. And thereby, there's no answer. Okay, so you're at this point. You have no question that started, but you have an answer. So what's the tactic that scientists do? They make up a question that can answer this question, that's this answer. And this becomes a research article. Yeah. So, because this kind of became like the general episode of how these research articles are being published these days, in my view, it's very difficult to follow the thought process. I don't have a good like opinion of how the research articles should be written, because going through all this thought process might be very exhausting to read, right? the opinion that I have is that even in like nature journals, there is a section called like news and views, which kind of is a very short article written by another expert in the field that explains this discovery. So maybe this type of non-article yet scientific writings can improve to follow this thought process. Okay, the second implication that I wanted to make is that this Kuhn's idea of paradigm shift is closely related to anti-realism. Okay, so what is anti-realism? This is the official logo of Harvard, which says Veritas. Does anyone know what this means? Truth. Yes, truth. Anti-realism is a saying that there is no truth. And even if there is truth, we cannot connect to it. He says scientists can never truly understand the real world. The reality is ultimately unknowable. Any attempt to describe it obscures as much as it illuminates it. And science does not evolve toward anything, but only away from something. What it means is that you might recall like this time alternating view of normal science and revolutionary science. Where do you think this is headed? Does it have like a ultimate goal? Maybe a Veritas? But Kuhn says that no, it is not evolving towards Veritas because there might be no Veritas at all, but even if it was, we have no access to connect to it. So we are just evolving to another stage that is different from the previous stage. That's all we can say right now. There is another very famous analogy in the philosophy of science which says that what we know is colored as blue, and what we don't know is colored as white. So what we don't know lies in the edge of what we know. The more we know, the more we also don't know, which also means that it is never possible to be closer to truth, even if truth exists. Okay, switch gears and let's talk about some criticism, some skepticism that people have about Kuhn's theory. People say, okay, Kuhn says that most of our work during normal science might not translate into the next paradigm shift. He also says science may well enter a phase of permanent normalcy. Okay, so what this second sentence says is that maybe there is no more paradigm shift in the future. Maybe we have already reached the plateau of normal science, because that doesn't contradict with Kuhn's theory. The first sentence says that the active normal science we are doing now might be just useless after the paradigm shift. So the whole concept of this skepticism is that, where do we find the motivation to do science? Because all of this skepticism, all of these things seems very unmotivational to do new science. Right? We can kind of recover from this skepticism by looking at some examples. So take a look at the first sentence, which was most of our work during normal science might not translate to the era after the paradigm shift. Okay, this is the stages, stages in different time zones where the Eiffel Tower was getting built. Okay, so it was built between 1886 and 1889. It took about 2 years. But in the middle, you can see these intermediate bridges, right? Which doesn't show in the very end. Okay, so what this concept of foundationalism says is that all our knowledge is built upon foundation of building blocks. Maybe what we are doing in this normal science era is just building blocks, right? But would you say like this building block was useless at the end? No, right? Because it was crucial to have this Eiffel Tower in a high yet hollow state. So even if it might seem that normal science, the building blocks that was made during normal science, seems to be useless in the end, it was very important in the creation of new knowledge. Another example that we can think of is actually very simple. What kind of physics do we use when we launch spaceships? Do we use quantum mechanics? No, we actually use Newtonian physics even till this day, right? So we still use Newtonian physics to launch spaceships, even though the paradigm shift has made from Newtonian physics to new type of physics. So this is basically saying that sciences in different paradigms can be used for different purposes. So it is not that all becomes useless, but it can be used in different purposes. Going back to the second sentence, which said that science may well enter a phase of permanent normalcy, maybe it might be true. Maybe we wouldn't have another paradigm shift. But even so, having a normal science era is very important to have technological advances. Because when we recall like the definition of Kuhn, definition of paradigm that Kuhn made, he emphasized on practitioners, right? Because we can view that even with the end of the paradigm shift, a lot of technological advances can be made, which both can kind of lead us to be motivated to do science again, right? Going on to the very last part of the topic. The last skepticism that people have is the side effects of having a monopoly of a single paradigm. So Kuhn said that there can be only one paradigm within an era. There cannot be two existing paradigms. There can be only one paradigm. This is actually a serious point that people cannot, defend Kuhn, because Kuhn, I don't know why, but Kuhn kind of depicted the communist scientists as the paradigm addicts. He even made an analogy with the brainwashed characters in Orwell's book. So that's how much scientists in the normal science era are immersed in the paradigm. So what are some side effects? There is a great example of the side effect that has already occurred, which is the observation of supernova. According to record, in Asian countries, the supernova was observed in the year 185. But in Europe, the first literature that says they observed supernova is in the year 1572. Would it be because Europeans had a less development of observation? Probably not, right? It's because in this era of Europe, they were under the Aristotelian paradigm, which says that the cosmos beyond the moon and planets was immutable. Immutable meaning nothing can show up, nothing can emerge, nothing can disappear. It just stays the same. So in Europe, because the people there were brainwashed by this Aristotelian paradigm, it took them more than 1,000 years to actually discover this observation as a meaningful data. Oops. Okay, so how can we kind of modify Kuhn's view? This is a picture of a traffic jam. When we think of why traffic jam happens, it's because all the cars are going in the same direction. Right? It's all starting from here, and they all want to go here. They are under the same one route of the path. But what if there are multiple paths? Then it can then it can have like less traffic jam. So this idea of pluralism is a state where two or more paradigms coexist. And many people have been supporting this idea of, it is true that we are in an alternating phase of revolutionary science versus normal science, but during an era, maybe, there might be two or more paradigms existing at the same time. One advantage that we can take by having multiple paradigms at the same time is that we can also have a major technological advance as well. This might be a little bit different example, but when we look at the GPS system, it not only uses Newtonian physics, but it also uses Einstein's relativistic theory, which is two very different paradigms, right? So if we are living in a stage where like two different paradigms coexist, they might, make up a totally new technological advance that were not possible to be made within a monopoly of a single paradigm. Okay, so recap of part 3. There were two implications of Kuhn's view. One was that the history of science should be viewed very importantly, and we should follow the thought process. The second one was the implication to anti-realism, that there is no reality in science. In the later part, we talked about the skepticism about Kuhn's view, about how it unmotivates us to do science, but we can kind of recover from that. But the brainwashed scientists under one single paradigm, this kind of moves the field towards having a pluralism, having multiple paradigms at the same time. Okay, so that's about it. Thank you very much, everyone.
You finish with some more questions.
Or we can break, and if you have questions for me, you can come up and talk to me after the fact. Thank you everyone for attending tonight's lecture.
And a reminder that next week at the same time, the same place, we will have another talk. And
Actually, I have one question for
Oh,
you, Yoony, on
yeah.
the YouTube channel.
Oh, all right.
Someone from Pittsburgh wants to know, was there any intended reason for Kuhn to argue that previous normal science becomes useless after a new paradigm?
Yeah, that brings the whole concept of incommensurability. Okay, where should I? Okay, hi. Thank you for the question. So Kuhn basically said that like two different paradigms cannot talk to each other because they talk in a totally different language. So that's why the normal science under the first paradigm might not be translated to the next era because it uses a totally different language and it is a totally different view, if that answers your question.
There's just a tiny bit of delay.
Thank you for coming. Right. Actually, it's up like that, right?